Morning. My name is Jared. I'm a first-year graduate student over at Princeton. And today I'm excited to share some new perspectives on stellar activity detrending with an emphasis on how we can reapply some existing spot models. When discussing stellar activity, I think it's always fitting to begin with figures such as this, A, because they are cool, and B, because they can teach us a lot. So for something like this, on the top, we're just plotting STO images of the sun in H alpha, and below is the corresponding rate of velocity from Harps North. And this tells us two things. First, stellar activity is hard. There's a lot going on the stellar surface, but also it gives us hope because we can visually correlate what's happening on the stellar surface with the rate of velocity time series below. And often, all of this complex physics on the stellar surface is simplified into a single spot model that takes into account two main effects: the fact that stars are rotating and the fact that sun-like stars have convective envelopes. Many of you will recognize this as the FF prime framework, which I'm briefly going to give a background on. So when we consider stars, we can look at them through the lens of rate of velocity. Essentially, how does a stellar disk look from a rate of velocity perspective? So first, stars are rotating. That means that one hemisphere is going to be blue shifted towards us, while the other is red shifted away. In a simplified framework with no differential rotation, sorry, Sarah, that means that we can simply describe the star as a function of longitude and latitude. So that's half the story. The other half is the fact that there are large convective cells rising towards the surface that creates a net convective blue shift effect, shown here. So none of this is actually time dependent. If this is all that there were on stars, you would have a really great time. The problems come from active regions, spots, and their associated magnetic regions. As they move across the stellar surface, they introduce perturbations to this rotation rate of velocity signal and the convective rate of velocity signal. And the result will be something like this, where on the x-axis, we're plotting the rotation phase of the spot complex, and the y-axis is the convective perturbation and the rotation perturbation. The little graphic there is showing the location of the spot at that point on the phase curve. To make it a bit more clear, we can add another one. To make it even more clear, we can add eyebrows and have a fun face. I think my parents are planning to watch this, so I really hope they're proud of me. So we combine all of this together, including the eyebrows, into the commonly known FF prime model, as shown here. Essentially, using this simplified geometry, we are able to relate the convective and rotation perturbations with flux in the first derivative of flux. So this is a very powerful framework, and one of the ways we can see that is by looking at this NUID GTO target. So this is a solar type star. It's being discussed by, I believe, about 5 people at this conference. So the rest of you also hop on the train. It's a very cool star. So we have here about a 100-day span of data with a clear quasi-sinusoidal signal. So what we can do is we can take this data, we can apply the standard FF prime framework, and we get a model such as this. In this case, we actually do not have simultaneous photometry. So we're using a flux proxy instead. We're using the depth metric introduced in a prior paper. It's essentially analogous to the CCF contrast. So this is wonderful. We have physically motivated activity detrending. I can now end my talk, except we have a wish list of about 3 things remaining. First, time derivatives are hard. A, from a math perspective for me personally, but also B, it requires extremely high observing cadence. So can we somehow remove that need for a time derivative? Second, flux is great, but it is not our main rate of velocity data product. In fact, we tend to work with things like the one-dimensional spectrum or the cross-correlation function. And lastly, this model is still great, but a lot of the free parameters are very difficult to interpret in terms of the physics of the star. So how can we solve that? Hopefully we can. And the way we're going to do it is using formation temperature. So there was a great series of recent papers diving into this. The next talk is going to tell you even more about it. So I will hope to do it justice. The general idea is that if you imagine a cross-correlation function or a simple line profile, when you're near the wings of that line, you're going to generally be considering hotter formation temperatures than when you are at the core of the line, or vice versa. The wings of the line have to do with deeper parts of the star than the core. And it's been shown through empirical evidence that when you calculate the rate of velocity at higher formation temperatures, so just only using the wings, there's a much stronger correlation with the convective component of the rate of velocity signal. So that's a wonderful trend. And in fact, our NUID GTO target shows this in incredibly high precision. So what we're doing here is we're first calculating the rate of velocity using just the wings of all the lines. We then calculate another rate of velocity time series using just below that, and so on. So to read the x-axis here, a depth of 0 means we're at just the wings. A depth of 1 means we're just using the very bottoms of the lines. And we see a really wonderful result, which is that using the result of our FF prime model to essentially have an idea of what the convective and rotation perturbation should look like, we see that the wings of the lines are nearly 1-to-1 correlated with the convection signal, while the bottoms of the lines are nearly 1-to-1 correlated with the rotation signal. That's already a wonderful physical result. There's a lot of things that can be done here. Instead, I'm going to switch the slide. I'm going to talk about how we can leverage this into an updated version of the simplified spot model. Take the simplifying assumption that we are only considering a rate of velocity time series with one of 3 sources. It either has a Keplerian signal that we wish to study, it has a rotation perturbation, and it has a convection perturbation. We're then going to calculate 2 new rate of velocity time series, one near the wings of the lines or the wings of your CCF, and the other using the core. The idea being that from what we just saw, these 2 new rate of velocity time series will each have different contributions from the convective and rotation perturbations. We then take the difference. We have something that looks a lot like the bisector inverse slope, except we've now written in such a way that these coefficients can be directly mapped back to formation temperature using something like a stellar atmosphere model. With a little bit of algebraic magic, we arrive at an updated version of the FF prime model, very similar to what was seen in Rajpal 2015. But in our case, we're again approaching it directly from the formation temperature perspective. So have we fulfilled our promises? First, there is no time derivative. That is great. That means that we can now apply this across a wide range of observing cadences. Second, we see that this can be calculated using our standard observables from rate of velocity, things like CCFs in the 1D spectrum. And that's by taking advantage of the fact that there are many flux proxies. So we're able to use this across a wide range of archival data into the future. And lastly, a lot of these coefficients can be directly mapped to things like how much stronger is the convection in your rate of velocity time series 1 versus 2, essentially your high effective temperatures versus your cool effective temperatures. So does it work? At this point, I sincerely hope so. Here we have about 100 days of NUID solar data with a clear rotation modulation signal. And we take our model we just derived. It's essentially just a linear combination of the CCF contrast with these 2 new rate of velocity time series, one from the wings, one from the core. We see it does a wonderful job of mapping the overall behavior. So that by itself is great. We're beating linear regression. We're beating the original RMS. That's wonderful. But that's not our whole goal. Our goal is to understand the actual sources of activity. So to do that, we can try to turn to the back of the book to look for the answers. Because we're looking at the sun, we can take advantage of the Sol-Aster pipeline. It takes spatially resolved images of the sun and calculates the convective perturbation and the rotation perturbation. So can our model match these signals as well? Thankfully, yes. This means that we are not only having incredibly high signal activity detrending, but we are also recovering actual signals from convection and rotation, which is really cool. As even more proof that you should take this seriously, this is our original NUID star. We're again just applying this simplified model. All of this runs incredibly quickly. We're not using GPs. It's just really a linear combination of the things that we already have from our CCFs or 1D spectrum. So that's great. So far, we've essentially shown that you can take the FF prime framework, combine it with information about formation temperature to arrive at this new way of thinking about the spot model that is meant to be physically motivated. So what can we do with this? There's many things. I'm excited to talk to many people about the other things we have not thought of yet, but here's one example. You can ask questions using this model, like how much stronger is the rotation perturbation at one part of the CCF, or one range of formation temperatures, relative to another part. The reason you might want to ask questions like this is to inform future activity models, but also stars are cool and we should try to understand them as best we can. So what we can do is we can select 2 regions of the CCF. This gray band will be kind of our very cool formation temperature region. The blue band is slightly higher up, so slightly hotter temperatures. And what the model does, it just tells us how much stronger the rotation perturbation is in the gray band relative to the blue. In this case, they're quite close together, so the answer is a small perturbation, especially per second. But if we move the blue band up, we see that that difference increases. And if we repeat this process over and over, we can create a plot like this. What we've done here is we have mapped the strength of the rotation perturbation as a function of position in the cross-correlation function. And again, using a stellar atmosphere model, we can convert this x-axis, which in terms of depth in the cross-correlation function, we can convert that to things like average formation temperature and average radial position within the star. This is opening the door to a lot of exciting physics, which I'm excited to talk to lots of folks about. You can do this again also with the convective effect. For that, I'll leave out my conclusions, which is essentially we've revisited the FF prime model from a formation temperature perspective. And a lot of the benefits are things like this works just with all of our data projects that we have. Everything I've shown here is just using the CCF or the 1D spectrum. There is no need for that first derivative, so there's very relaxed cadences. And lastly, it's physically motivated. What I showed in the last slide is just the beginning. There's a lot of fun stuff we can do. Thank you.
Thank you, Jared, for an interesting and on-time talk. Let's take questions. Lauren's got her hand up here.
Hi, Jared. Lauren Weiss, University of Notre Dame. This was an awesome talk. And between your talk and Sarah's talk, I'm convinced to abandon GP models forever. So I guess I have two questions for you. One is, what do you assess is the predictive power of this? Your slide where you sort of reproduced those new RVs was astounding. I'd like to understand a little bit more about to the extent to which that was a prediction versus a tuning. And my follow-up, or a totally unrelated second question is, what range of temperatures of stars is this method applicable for? Just G and K type stars, or will it work for M dwarfs?
Yeah, so to answer your first question about the level of tuning, so there is no tuning in a plot like this, if it'll actually show. So all we're just doing is fitting the model. And as part of that, it just gives us what it believes to be the convective component and the rotation component. So this is just straight out of the model. The second part about predictability, the one limitation here, it's the same as just the standard FF prime model. And that is if the spot fraction is changing as a function of time, that just means we need to introduce time dependence into the free parameters, which really just means that we can take this, couple it with GPs, and we're off to the races. We have a lot of fun physics to start doing. M stars, yeah, should be in the works. It's a bit harder to actually do the mapping between line depth and formation temperature. That does not mean it's not possible, but it just means that more work has to be done.
Hey, really cool talk. Also, I kind of love that it's a sort of come full circle. So I gave a talk yesterday looking at gave a little overview of the history of how we ended up using GPs on radial velocities, and actually started with the FF prime method. So it's quite cool that we've come back to this like a decade later. My question is, how sensitive is this to your model of your line temperatures? So you're choosing which of the the different depth ones based on a model. How sensitive is this to that model? And again, could we use this as a, hey, fine tuning, or maybe the star is actually this model rather than this model because it matches the data better?
Great question. The initial assumption of the model is just that when you pass in these two radial velocity time series, all it cares about is that they have different contributions from the convective and rotation components. The reason you start caring, though, about how carefully you draw these lines, like what parts of the CCF to use, has a lot to do with signal to noise constraints. So you want to use as many photons as possible. So that's kind of one constraint. But on the other hand, as you want to make these temperature regions as different as possible, so the magnitude of the difference is larger. Right now, this runs so fast that we just have it iterate over a grid of different regions on the CCF to use, and that will run in about a minute for all the solar data.
Questions? Okay. All right, well, let's thank Jared again.